College. I've been on the team for 2 years, and I'm experienced in the mechanical and electrical design of the UAS. I'm the team lead for the MCC drone design team, and I oversee the overall development of the new system. On the flight line, I will be directing all sub-team leads for competition readiness and overseeing the general readiness of the UAS.
Hello, I'm Spencer Arnold. I'm a sophomore at MCC. It's my first year on the team. I have experience with electrical and mechanical systems. I am the electrical lead this year. I oversee all electrical components necessary for the new system. And on the flight line, I will be overseeing the readiness for all electronics and power systems.
Hi, I'm Patrick Chernowski. I'm a freshman at Monroe Community College with 1 year of experience on the team. I have experience in the mechanical systems of the UAS. This year I'm the mechanical lead for the drone design team, and my responsibility on the flight line will be to make sure that the mechanical system pre-flight checklist gets done.
I'm Hussein Hamdan. I'm a sophomore at MCC, and this is my first semester on the team. On the team, I was responsible in developing and testing the object detection, location, and classification program. On the flight line, I'm going to be responsible for ensuring manual detection goes smoothly and all the images are properly submitted into the interop system.
I'm Luke Petterson. I'm currently a sophomore at Monroe Community College. I've been on the drone design team for 2 years. I was the previous team lead, and I'm responsible for the avionics and autonomous flight implementation. On the flight line, I will be the safety pilot for our drone.
My name is Marcus Milton. I'm a freshman at Monroe Community College. I have 1 year of experience on the team doing mechanical design. On the flight line, I will be helping go over the pre-flight checklist for the UAS and operating the manual object detection system.
I'm Madison Brewer. I'm a freshman at MCC with 1 semester of experience on the design team. I'm responsible for designing mechanical components and researching some things. And on the flight line, my responsibilities will be safety and repairs in emergencies if needed.
Hi, my name is Joseph Corbelli. I'm a sophomore at MCC. I've been on the UAS design team for 2 years. This year, I've primarily helped with the payload design. In the past, I've helped with the electrical systems. On the flight line, I will be in charge of making sure that the payload is ready before flight.
Hello, I'm Yaroslav Kifor. I'm a sophomore at MCC. I lead the software sub-team. I'm experienced with the design of object avoidance and object DLC systems. This is my first year on the drone design team. On the flight field, I'll be operating communication systems and preparing the base station for use.
Hi, I'm Will Gardner. This will be my 2nd year on the drone team. I am a sophomore at MCC. I am responsible for maintaining smooth interoperability between the judge server and the client server on our side, and I also contribute to programming and server design.
For our planned mission demonstration tasks, we will be attempting all tasks except autonomous image submission. We are very confident that our system will capture all waypoints during autonomous flight and complete a successful air delivery drop. For our obstacle avoidance system, we are confident that the system will avoid all stationary objects and most moving obstacles. Due to a restricted timeline, the team was unable to produce an automatic detection system, but instead will be implementing a manual detection system. Since this is the first time the team will be attempting object DLC, we are confident that the system will at least capture 2 of the ground targets.
Our UAS is a conglomerate of mechanical, electrical, and software-based systems operating together to meet mission requirements. For our flight controller, our team has employed a PixHawk 2.1, which helps control our motors and communicate with the Tyrannus transmitter over a 2.4 GHz radio link. The PixHawk also uses an RFD 900X to communicate telemetry via 900 MHz radio signal back to base station, which in turn communicates with the interop servers. In conjunction with the PixHawk, an Odroid is used to handle image processing and planning paths to avoid potential obstacles. Images and objects are sent from the Ubiquity bullet and our base station bullet, which communicate via a router to the interop server. Images take an extra stop through a computer tasked with processing images to find the necessary information about targets, their location, and their properties, which are then submitted to the interop server.
This year we developed an H-8 copter design based off last year's H-frame quadcopter design. The system has a thrust-to-weight ratio of 1.5 to 1 and weighs a total of 11 kilograms when all systems are attached. For our air delivery, we decided to go with a winch delivery system. We will be using a small fishing reel to lower the payload. The rationale behind this decision is that we have the ability to adjust the speed of the drop while keeping the system relatively light. The payload will have a harness that is attached to the fishing line, and a servo motor will hold the payload in place until delivery begins. Upon release, the payload will be lowered at a fixed velocity due to the drag from the fishing reel. We will be using two Tatu 12,000 mAh batteries in parallel to get 24,000 mAh at 22.2 volts. This will allow the system to achieve 20 minutes of flight. The system uses 8 MN4014 400 kV motors and 17-inch propellers in the coaxial stacked configuration. This configuration gives the copter greater thrust per unit volume, allowing for the vehicle to carry more weight without significantly increasing the size of the copter. We will be using a 3-axis gimbal with a Sony a6000 to take pictures from the UAS. The 3-axis gimbal allows for us to take pictures from any angle, which significantly increases the chance of our image detection system finding targets on the flight field. A Ubiquiti M2 bullet and a 9-gain antenna are used on the UAS to communicate images down to the base station. In our testing, we found that images are effectively transmitted and received from a maximum distance of a half a mile.
Images are taken by the Sony a6000 camera and sent back to the base station by our Ubiquiti bullet. The 24 megapixel images are taken and transmitted once every 7 seconds, with an image being received at the base station in about 8 to 20 seconds. From testing, we have found images need to be processed by an operator in about 10 to 12 seconds. From there, a web app was developed to assist operators in finding and classifying images. An image found to not contain a target is thrown away. If an image does contain one, it is sent out for further processing. To process through the images and find targets, the images are split into its separate color channels and transferred to the YUV color space, before using an algorithm to threshold and detect targets. Images that are identified as containing a target use the center of the object, telemetry from the drone, and trigonometry to detect its location. A program was created using Python and DroneKit in order to help us achieve the goal of avoiding obstacles this year at competition. Obstacles and waypoints are going to be received from the interop servers and transmitted to our drone in order to be plotted so that appropriate actions can be taken. Every 0.5 meters are going to be traced by our algorithm in order to find any potential obstacles in the way. Once an obstacle is found, a quick calculation is done based on the position of the UAS in regards to the center of the obstacle, and a new waypoint is placed, allowing our UAS to circumvent the obstacle. In this example, you can see the original path that we plotted and intended our UAS to complete autonomously for a mission test. The second image shows the new path taken by our UAS after taking into account the virtual obstacles we imposed upon it. The new waypoints were plotted, they were circumvented, but the same mission was completed. In order to make the most of our limited time during the developmental testing phase, we took multiple steps to make sure our system would be fully tested by the time competition came. First, we prototyped an H8 configuration on a smaller scale UAS with the intention of eventually implementing this configuration onto a larger frame, which we will be bringing to competition. After testing the H8 configuration, we began progressive safety testing. For us, that meant making sure that it could initially fly, and making sure there was no problems with manual flight, and then testing autonomous flight. And in the event that something would go wrong with an autonomous flight, testing to ensure a manual operator could take over and safely land our UAS. After we finished up initial testing to make sure that our UAS was safe to fly, we started giving it autonomous missions and testing our onboard obstacle avoidance. As soon as we were certain that was working, we moved on to obstacle avoidance using gazebo simulated testing. And then finally, we began object DLC control testing.
For the developmental testing of our autonomous flight system, the MCC drone design team conducted 23 autonomous flights using the Pixhawk 2.1 flight controller and HERE GNSS GPS on our competition platform. The autonomous flight system performed well for a large majority of flights, causing the safety pilot to only take over during 2 of the missions. This resulted in an average of 23 seconds of manual flight per autonomous flight. On the Lilac Heavy platform, 23 autonomous flights were conducted, with 5 being full mission tests, 10 being air delivery drops, and 8 being waypoint capture specific. This resulted in 116 waypoints being attempted, with 109 being hit within plus or minus 2.3 meters. Since our prototype platform uses the same autopilot system as our competition platform, we used the prototype H8 platform to gather data on waypoint accuracy. 15 autonomous flights were conducted on the prototype system, with a maximum of 5 waypoints per mission. This allowed for the team to seamlessly gather data on waypoint accuracy on a small scale that was easily repeatable. A total of 73 waypoints were attempted on this system, with 70 waypoints being captured at an accuracy of plus or minus 2 meters.
Due to the decimeter level accuracy of our 3D GPS, the PX4 autopilot system, and the use of our in-house code created to avoid obstacles on the O-Droid, we found a very high level of navigation at our disposal. During developmental testing, we found we missed most, if not all, targets, and we have full confidence that we will perform this well at competition. Any improvements we made during this phase was either alterations to our code to make it run better, or just slight tweaks to the autopilot to ensure everything ran smoothly.
Full mission tests were conducted in a fashion that was similar to the 2017 SUAS competition format. Each full mission test included 6 waypoints to capture, 1 air delivery drop, 2 stationary virtual objects, 1 moving virtual obstacle, and 5 ground targets. 5 full mission tests were conducted by the team, with the system performing as expected. On average, the UAS captured 5.5 waypoints per mission, identified 2 ground targets, avoided all stationary objects, and 80% of moving obstacles. For each full mission test, the UAS also successfully dropped the payload on the designated GPS coordinate within reasonable uncertainty. Flaws detected during the full mission tests include inconsistencies with the moving obstacle avoidance code and stability issues regarding the camera gimbal. The camera gimbal needs to be tuned properly for the speeds that the UAS will be operating at to increase the stability of the camera. The obstacle avoidance system will continue to be tweaked to allow for the UAS to more precisely navigate around obstacles. Once the system made its way into the air, generic PID tuning was conducted to allow for the safety pilot to operate the UAS safely. Following this process, the auto-tune feature was used in Mission Planner to prepare the system for autonomous flight. After the initial tuning processes were complete, a manual maximum speed test was conducted to determine what speeds the UAS was capable of, and from this data, an optimum flight speed was selected for autonomous flight. During the first few autonomous flights, autonomous takeoff and landing was sufficient for the team and no tuning had to be conducted.
When testing our imaging system, 3 things were kept in mind: the amount of targets that we laid out for it to capture, the amount of images taken, and then ultimately the amount of targets detected. All 3 of these would greatly impact our ability to accurately and quickly process images during competition. During testing, we also collected data on the average resolution of targets that were returned from our system, as well as the overall quality of pictures that would be submitted for processing. What we found is that both factors were minimal in impact on our overall performance because of the high resolution of the Sony a6000 as well as the stability of the gimbal we were using. We also tested our object detection and classification performance. We needed to ensure before competition that we'd have competent operators who are familiar with the program we developed in order to assist manual detection. During our mission tests, we had multiple operators working on multiple sets of pictures in order to test what would be the most efficient way to process images during competition. And what we found in the end was we needed as many people as possible working on image detection at a time. The more people we had, the faster we would go through images, find targets, and be able to submit them to the server. The only limitation to this is we need to balance this with the amount of people on our team. Having such a small team, taking someone away to work on object detection and classification would mean 1 less person on the flight line to make sure everything operates smoothly. And what this means for our team is during competition, at max we may have 4 operators, but we're more likely to only have 3 during the actual flight of our UAS.
For our air delivery system, we conducted a series of tests in which our system dropped the payload from approximately 110 feet onto asphalt pavement. We completed 10 drops from approximately 110 feet. Out of the 10 drops completed, the bottle remained intact for 9 of the drops. We feel that the tests conducted accurately model the competition conditions and are confident with our air delivery system.
For our planned mission demonstration tasks, we will be attempting all tasks except autonomous image submission. We are very confident that our system will capture all waypoints during autonomous flight and complete a successful air delivery drop. For our obstacle avoidance system, we are confident that the system will avoid all stationary objects and most moving obstacles. Due to a restricted timeline, the team was unable to produce an automatic detection system, but instead will be implementing a manual detection system. Since this is the first time the team will be attempting Object DLC, we are confident that the system will at least capture 2 of the ground targets.
The drone we're entering in this competition this year is the culmination of the efforts of a small but dedicated team. Can't wait to present for you guys.
As a takeaway, I'm incredibly excited to see how our team stacks up against the other universities at the competition this year.
With all the effort we put in this year, I'm confident that we will perform better than last year. Thank you for watching our presentation. I hope you enjoyed it.